In a previous video, we saw that the greatest lower bounds and the least upper bounds were actually the same thing. So let us prove that. Okay, that's not obvious, it needs a proof. So it's a theorem. This is theorem 1.11 in the book. So let's say that S is an ordered set that has the least upper bound property. Okay. Let's say we have a subset B. Okay, that is non-empty. And let's say that B is bounded below. Typically in a theorem, you see all these assumptions that are ruling out the problematic cases, okay? Now, let's call L the set of all lower bounds of B, okay? In these circumstances, then alpha, that is the supremum of L, exists in S, and this is the important thing, the supremum of L is equal to the infimum of B. Okay, so this means, in particular, this means that the infimum of B exists in S okay, and therefore S has the greatest lower bound property. Okay. So this is the, I didn't like that. So this is the key point, maybe the most mysterious. So there is a relation between that supremum of L and the infimum of B. And because we are able to show that the supremum of L exists in S, then so does the infimum of B. And that is the definition of S having the greatest lower bounds property. So let's get into the proof. Now, let me show a little bit the idea. Remember, we have here our set L, which is the set of lower bounds, L for lower bounds of B. Okay, let's write it properly. So this is the set of y's in S such that y is less or equal than x for all x in B. All right. Now, let's do a picture. Even pictures in this case may be a little always false, but math is the art of doing proper reasoning with wrong pictures. So let's say this is our set B here, okay? And we want to find the infimum of B, okay? The infimum will be here. Now, the challenge is that we have the least upper bound property. Okay, least upper bound property, S has the least upper bound property. This means that subsets that are bounded have a supremum. So this is, let's say informally, this is good if I want to find a supremum. Let me write it again. Okay. Now, that's a bit problematic because we are aiming for an infimum, but the property we have is good for supremum. So there is a bit of a problem there. So the strategy is to think, okay, let me, so because I can find a supremum easily, let me work with a set that is next to B, but right below. Okay, so a set that is here. Okay. In such a way that I can find the supremum of this set that I just defined. Okay. So what is the set I'm talking about? So because B is bounded below, this set on the left is the set L of lower bounds. Okay, every element in this set, let's pick this one for example, is a lower bound for B. This one is a lower bound for B. All of them are lower bounds for B. Okay, so then this is a set that is also bounded above by B. Okay, because B is next to it, it's on the right. So the strategy is that, okay, we have a bounded set that is L. We are living in a space with the least upper bound property, so we can find the supremum of L. And then the question now is, well, since we are not living in any space, they are next to each other, really back to back, then we need to show, but it should be true, that the infimum of B equals the supremum of L. And we are good to go, because the supremum of L exists because of the hypothesis we have, and that existence transfers to the infimum of B. Okay, so that is the strategy, the game plan. Let's write it down in 2 steps. So first step, I want to show that alpha is the supremum of L. Okay, and it exists and it's an element of S, and this is because of the least upper bound property. Okay, and the step two is showing that alpha is actually the supremum of L is the greatest lower bound of B. That is the definition of alpha being the infimum of B. Okay. So these are the 2 steps we are going to take. So step 1. For step 1, we need to somehow use, the only thing we can use is the least upper bound property. Okay, so let's set things up. So we have our B that is bounded below. Bounded below. Okay, because it's bounded below, there is going to be some lower bounds. Okay, that means that the set of lower bounds is not empty. this we need. Okay. And in fact, if we look at the definition of the set L, I'll write it again. The element in S such that y less or equal than x for all x in B. Okay, what we notice is every element of B is an upper bound of L. Okay, so that means that L is bounded from what side? Bounded above. Okay, because it has upper bounds. And we are set. So look here, we have L that is non-empty, bounded above, and we have that S has the least upper bound property. Okay, so these three mean that there is a supremum of L in S. Okay, so this means, let's go back to yellow. This means that it exists and is in S. So we are showing two things here. We are showing that it exists, and we are showing that is a member, is an element of S. Okay, so this is step one. Showing that alpha, the supremum of L, exists and is an element of S. Now, step two. For step two, let me copy paste. We want to show that alpha, the alpha we just found, the supremum of L, is the greatest lower bound of B. Okay, remember the picture? Let me also bring that back. So we are going to follow the idea in the diagram. So we want to show that it's the greatest lower bound. So this, if you notice, has two parts, this statement. We need to show that it is a lower bound. And we need to show that it's the greatest. Okay. So there are two things we need to check. So 2.1. First thing to check is that that alpha is a lower bound of B. Okay, this means alpha less or equal than x for all x in B. Okay, and here you need to provide reasonable proof until it's completely clear. Okay, so notice, so in fact, if I take, so I want to show that it's a lower bound of x. So let me take some number x smaller than alpha, okay? And let me tell you then x cannot be an element of B, okay? Because x is not an upper bound of L. Here, remember, every x in B is an upper bound for L. Okay. Yeah. So basically, if you think about the diagram, so here you have your B. Okay, and here you have your alpha. So you cannot really say that you have some x in B that is to the left of alpha. Okay, that's what we are saying. It's clear, right? Now, the second part is to show that alpha is the greatest lower bounds of B. Okay, so for this, this is very similar. It's just consider another lower bound of B such that is strictly smaller, okay? And this cannot be. Similar to before, we have our set L. In this case, we have our alpha here on the right, and then we are saying that we have some beta to the left, to the right of alpha that is in L. That's not possible. If you want to be a little more formal here, beta, another lower bounds of B, that means that beta belongs to L. Okay, but then notice that alpha is the supremum of L, okay? And we are saying that some beta that is in L is strictly bigger than the supremum of L. That is impossible by the definition of supremum. They're saying that is larger than the largest. So by definition of largest, that cannot be. And this is it. So we have proved that alpha is the greatest lower bound of beta, of B, and that means it is lower bound of B. That means alpha is the infimum of B. And this finishes the proof.